Hello and welcome back. Tonight we're going to meet a traveler. Not someone from across town or even across an ocean. This traveler came from another star system entirely, drifting through the darkness between suns for billions of years before arriving, quite unexpectedly, in our little corner of space. Its name is 3I Atlas, and it's only the third visitor of its kind we've ever noticed. Before we begin, I'd love to know where you are watching from tonight, and how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy these videos, please consider subscribing. It helps more people find their way here. Now let's begin. 3I Atlas is the third known object from outside our solar system to travel through our neighborhood. The 3I prefix stands for Third Interstellar, a gentle reminder of how rarely such visitors appear. Think about that for a moment. The third, in all of human history, through every civilization that has looked up at the night sky, through every telescope we've ever built, through every dedicated survey scanning the heavens night after night, we've only confirmed 3 visitors from beyond our solar system. 3. The first was discovered in 2017, the second in 2019, and now, in 2025, the third. It's not that these objects are especially rare, necessarily. In fact, scientists suspect that interstellar wanderers drift through our neighborhood fairly regularly. But space is so impossibly vast, and these travelers are so small and dark that noticing them at all is like trying to spot a single snowflake in a blizzard from miles away. What makes 3I Atlas special isn't just that it's interstellar, though that alone would be remarkable. It's that we noticed it. Someone, somewhere, was watching carefully enough. A telescope in Chile, sweeping methodically across the sky, happened to catch a faint smudge of light that didn't quite belong. And from that tiny observation, we learned that we had a visitor. Perhaps that's the real wonder here. Not just that the universe is filled with wanderers, but that we've become skilled enough, patient enough, to occasionally see them pass by. We've learned to notice the things that don't quite fit the pattern. The strangers moving through a crowd of familiar faces. The designation 3I feels almost humble, doesn't it? Not the magnificent interstellar visitor or the astounding cosmic wanderer. Just 3I, Third Interstellar. Matter of fact, quiet. As if to say, yes, this is extraordinary, but it's also just what the universe does. It sends messengers. Sometimes we see them, usually we don't. And there's something peaceful in that, in knowing that the cosmos doesn't need our attention to continue its ancient patterns. These objects have been drifting between stars for eons, long before humans existed, long before Earth itself formed. They'll continue drifting long after we're gone. We're just lucky enough for this brief moment to watch. One passed by, so here it is. 3I Atlas, the third known messenger from beyond, not trying to impress us, not here for any particular reason, just passing through, following the invisible curves of gravity, the ancient momentum imparted by its birth system billions of years ago, sailing from one nowhere to another nowhere, and briefly, just briefly, crossing through our somewhere. It was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System, ATLAS, survey in Chile. A routine sky survey telescope quietly caught a traveler from another star system. July 1st, an ordinary summer day for most of us. Perhaps you were working or on vacation, or simply going about the small rituals that fill our lives. And somewhere in Chile, a telescope was doing what it does every clear night, looking up. The Atlas survey isn't designed to find interstellar visitors, actually. Its primary job is much more practical, more immediate. It's watching for asteroids that might pose a threat to Earth, scanning the sky methodically, night after night, cataloging every moving dot, looking for anything that might be heading our way. It's protective work, vigilant work, the kind of careful attention that rarely makes headlines, but keeps us safe. And on this particular night, in the middle of that routine scan, Atlas found something that didn't quite belong. Imagine the telescope as a patient guardian, sweeping its gaze across the same paths every night, learning the neighborhood, recognizing the regulars. Most objects follow predictable paths, orbits that have been mapped for decades, trajectories we can calculate years in advance. But every so often, there's a stranger, a dot of light moving just a bit differently, coming from the wrong direction, moving a bit too fast. That's what Atlas saw on July 1st. It's worth pausing here to appreciate the quiet miracle of this moment. The telescope itself doesn't know what it's looking at. It's just collecting light. Photons that have traveled through space, bounced off a small icy object, crossed millions of kilometers, pierced our atmosphere, and landed on a detector. The telescope dutifully records this information, timestamps it, and moves on to the next patch of sky. The realization comes later. Someone, a human, or perhaps an automated system trained to flag anomalies, notices that this particular dot doesn't match any known object. Its trajectory is wrong, too steep, too fast, not elliptical but hyperbolic, not bound to the sun but passing through. And then the questions begin. What is this? Where did it come from? How far has it traveled? There's something beautifully humble about the fact that we discovered an ancient traveler from another star system using a telescope whose job is basically to protect us from asteroids. It's like setting out to guard your front door and accidentally meeting an explorer from across the ocean. You weren't looking for them, particularly, but there they were. And because you were paying attention, because you were watching carefully, methodically, patiently, you didn't miss them. The Atlas survey has many telescopes scattered across the globe, all working together to keep an eye on our cosmic neighborhood. They're not glamorous observatories, they're workhorses, reliable, consistent, looking at the same sky over and over, learning what belongs and what doesn't. And on July 1st, 2025, one of these patient guardians gave us a gift. The third confirmed visitor from beyond our solar system. Not because it was looking for such a thing, but because it was looking carefully enough to notice when something didn't belong. Perhaps there's a lesson in that, in paying attention, in doing the routine work, the careful work, even when it seems ordinary. Because you never know when the universe might send a messenger your way, and whether you'll be watching when it arrives. Its official designation is C2025N1, but astronomers use 3I Atlas to mark it as interstellar. The name combines a comet label with an interstellar signature, part comet, part messenger. Names matter. Even in astronomy, where objects are often reduced to catalog numbers and coordinates, the way we name something reflects what we understand about it, what makes it special, what we want to remember. Let's unpack this visitor's name, shall we? Because it's actually telling us several stories at once. First, There's C2025N1. This is the formal designation, following the International Astronomical Union's careful naming conventions. The C tells us it's a comet, an object with a visible coma, releasing gas and dust as it approaches the sun. The 2025 tells us the year of discovery. The N indicates it was found in the first half of July. Each half month gets a letter. The 1 means it was the first comet designated in that half month, and Atlas credits the survey that found it. It's a bureaucratic name, really, precise, informative, but not particularly poetic. But then there's the other name, 3I Atlas, and this is where things get interesting. The I stands for interstellar, not from here, not bound to our sun, a visitor from somewhere else. And the 3 reminds us that this is only the third time we've conclusively identified such an object. Before 3I Atlas, there was 2I Borisov, discovered in 2019, and 1I Oumuamua, discovered in 2017. And what a strange visitor that one was. So this object carries both identities simultaneously. It's C2025N1, a comet, following certain physical rules we understand, behaving in expected ways. But it's also 3I, something that doesn't belong to our solar system at all, something that formed around another star, something that has been traveling through interstellar space for longer than our sun has existed. Part comet, part messenger. There's something almost poetic about that duality, isn't there? It's behaving like the comets we know, warming up as it approaches the sun, releasing gas, developing a coma, and perhaps a tail. In that sense, it's familiar. We understand this. We've studied hundreds of comets, but simultaneously, it's utterly foreign. It carries ice and dust from a completely different stellar environment. Its molecules formed in someone else's protoplanetary disk. Every atom in its tiny nucleus has a history that has nothing to do with our solar system. It's like meeting someone who speaks your language but grew up in a place you've never been, will never go. The conversation is possible, the grammar is the same, but every word carries echoes of somewhere else. Astronomers tend to use the 3I Atlas designation because that's what makes this object significant. Yes, it's a comet. That's nice. We have plenty of comets, but it's an interstellar comet. That's only the second confirmed interstellar comet we've ever seen. Remember, Oumuamua was more of an asteroid, or, well, we're still not entirely sure what Oumuamua was, but that's a story for another night. So when you hear the name 3I Atlas, you're hearing a story compressed into a few characters. You're hearing, this is special, this is different. This is one of only 3 times we've caught a traveler passing through. Pay attention. And yet, for all its significance, there's still that humble numbering system. Just 3I, not the grand interstellar visitor or cosmic messenger alpha. Just 3. We've seen 3 of these now. We'll see more. Eventually, perhaps, they'll become routine enough that the numbering seems quaint. But for now, in 2025, we're still in the early days. We're still counting them on one hand. Maybe that's fitting. Maybe visitors from other star systems don't need grandiose names. Maybe the simple designation, 3I, says everything that needs saying. You're not from here. We see you. Welcome. 3I Atlas follows a hyperbolic orbit, meaning it's not bound to the sun and will eventually leave our solar system. Unlike most comets, it sweeps in once, greets our sun, and then sails back to the stars. If you've ever thrown a ball straight up, you already understand the basic mathematics of orbits. The ball goes up, slows down, stops for just a moment at the peak, and then falls back down. It's bound to Earth by gravity. It will always come back. Now imagine throwing that ball so hard that it never comes back. It keeps going, moving fast enough that Earth's gravity, while pulling on it forever, can never quite slow it down enough to return. The ball escapes. That's approximately what's happening with 3I Atlas, except instead of escaping Earth, it's escaping the Sun. Most comets we see follow elliptical orbits. They're bound to the Sun, even if loosely. They swing in from the outer solar system, make a close pass by the Sun, relatively speaking. Close, in this context, might still be millions of kilometers, and then swing back out again. They'll return eventually, maybe in a few years, maybe in thousands of years, but they're ours. They're part of the solar system's family, even if they spend most of their time in the distant suburbs. 3I Atlas is different. Its orbit is hyperbolic. If you were to draw its path through space, it wouldn't form a closed loop. It would form an open curve, coming in from one direction, bending around the Sun due to its gravitational influence, but never quite turning back. The Sun pulls on it, certainly. It affects its trajectory. But 3I Atlas is moving too fast. It was already moving too fast when it entered the solar system, carrying momentum from whatever gravitational encounter ejected it from its birth system billions of years ago. So it will leave. It must leave. It's not a choice, exactly. It's just physics. The Sun cannot hold it. There's something bittersweet about that, isn't there? This ancient visitor, traveling for billions of years, happens to pass through our neighborhood for just a brief moment. We get to see it, study it, wonder about it, and then it will leave, sailing back into the vast darkness between stars, and we will never see it again. Perhaps it will encounter another star system eventually, in 100,000 years, or 1,000,000, or 10,000,000. It might drift close enough to another sun to be briefly illuminated, briefly warmed. Maybe that star will have planets. Maybe one of those planets will have civilizations that have learned to watch the sky. Maybe they'll spot this small, icy visitor and marvel at it as we're marveling now. Or maybe it will drift forever through empty space, never again coming close enough to anything to matter. We don't know. We can't know. The galaxy is vast and the paths between stars are long and dark. But for now, for this brief moment in cosmic time, it's here, visible in our telescopes, close enough to study, close enough to wonder about. A visitor that will stay only as long as physics allows, which is to say, not long at all. Most comets we study, we know we might see again. There's a cyclical quality to them. They're part of the rhythm of the solar system. But with 3I Atlas, there's a finality. One pass, one chance, then back to the stars. It's the astronomical equivalent of meeting someone extraordinary while traveling. A conversation at a train station, perhaps, or a shared meal in a foreign city. You know, even as you're talking, that this moment is temporary. You'll go your separate ways. You'll likely never meet again. And maybe that makes the moment more precious, not less. The fact that it's fleeting doesn't diminish it. If anything, it sharpens your attention. You're more present because you know it won't last. 3I Atlas sweeps in once, greets our sun with a flash of sublimating ice and reflected light, and then sails back to the stars. No return visit, no encore. Just this one chance to see a fragment of another star system, passing through our own, and then continuing its eternal drift through the space between suns. It came from somewhere we cannot see. It will go to somewhere we will never know. And for this brief moment, it's here, in the middle, visible. A messenger with no message, except perhaps this. The universe is full of wanderers, and sometimes, if you're watching carefully, you'll see one pass by. Only 2 other interstellar objects have been found before it. 1I Oumuamua in 2017 and 2I Borisov in 2019. Each discovery is like finding a cosmic postcard from a faraway solar nursery. Let's talk about how rare this is. Really rare. Humans have been watching the sky in a systematic, scientific way for about 400 years now, since Galileo first turned his telescope upward. In those 4 centuries, we've cataloged millions of objects, stars beyond counting, countless asteroids, thousands of comets. We've mapped the positions of planets, tracked the movements of moons, identified gas clouds and galaxies, and all the varied architecture of the cosmos. And in all that time, in all that searching, we have confirmed exactly 3 interstellar visitors. 3. The first was 1I Oumuamua, discovered in 2017 by the Pan-STARRS telescope in Hawaii. That was a strange one. Elongated, tumbling, behaving oddly. It caused quite a stir. Some scientists suggested it might be a strange type of comet. Others proposed it was an icy object that had lost its volatiles. There were even speculative, though unlikely, suggestions about artificial origins. We still don't entirely understand Oumuamua. It passed through too quickly, and we weren't quite prepared to study it thoroughly. By the time we realized how special it was already leaving. The second was 2I Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, using his homemade telescope in Crimea. Borisov was more comprehensible. It looked and behaved like a comet. It had a coma, a tail, the works. It was clearly releasing gas and dust as it warmed up near the sun. In that sense, it felt familiar, even though its chemistry turned out to be subtly different from solar system comets. Borisov was easier to study because we had a bit more warning, and it stayed visible a bit longer. But it, too, eventually faded from view as it sailed back out into the dark. And now we have 3I Atlas, the third member of this very exclusive club. Think about what these objects represent. Each one is a sample, a tiny precious sample from another star system, another place where planets might have formed, another collection of dust and gas that collapsed under its own gravity billions of years ago, forming a new sun and perhaps worlds around it. These interstellar visitors are fragments from those distant events, ejected by gravitational interactions and sent wandering through the galaxy. They're like postcards, as the saying goes, except imagine a postcard that took billions of years to arrive, that was never addressed to anyone in particular, that carries no writing but tells its story through the molecules frozen in its ice, through the ratios of its elements, through the way it responds to sunlight. Each discovery teaches us something. With Oumuamua, we learned that interstellar objects can be strange, stranger than we expected. With Borisov, we learned that some interstellar comets look quite familiar, suggesting that comet formation might be fairly universal. And with 3I Atlas, we're still learning. The data is still coming in. The observations are ongoing. But already it's adding to our understanding, giving us another data point in the grand catalog of how planetary systems form and evolve. The rarity of these detections tells us something important, too. It tells us how difficult it is to spot these visitors. Space is dark. These objects are small. By the time they get close enough to see clearly, they're already leaving. It's like trying to census travelers passing through a city by only watching one street corner. You'll catch a few, but you'll miss most of them. Scientists estimate, based on statistical models and what we've seen so far, that interstellar objects probably pass through the inner solar system fairly regularly, maybe several per year. But seeing them? That requires luck, excellent surveys, and quick follow-up observations. So every time we catch one, it's special. It's a reminder that we're getting better at this. Our telescopes are improving. Our surveys are more comprehensive. Our algorithms are better at spotting anomalies. Slowly, carefully, we're learning to notice the strangers passing through. Maybe someday we'll have detected dozens of these visitors, maybe hundreds. Maybe the discovery of an interstellar object will become routine, almost mundane. But for now, in 2025, we're still in the early days, still counting them on one hand, still feeling that spark of excitement each time we spot another cosmic postcard drifting through our neighborhood. 3 confirmed visitors, 3 chances to see beyond our own solar system without leaving home, 3 fragments carrying stories from places we'll never visit, 3 reminders that the galaxy is vast, active, and occasionally generous with its secrets. Observations show 3I Atlas releasing gas and dust, confirming it behaves like an active comet. As sunlight warms it, frozen materials gently sublimate into a glowing halo. For billions of years, 3I Atlas has been cold. Not just winter coat cold, not just frozen lake cold. Cold in a way that's almost impossible to comprehend. The cold of deep space, where temperatures hover just a few degrees above absolute zero. In that darkness, far from any star's warming touch, its ices remained perfectly preserved, frozen solid, inactive, silent, and then gradually things began to change. As 3I Atlas entered our solar system and began its swing past the sun, light began to touch its surface for the first time in how long? We don't know exactly. Perhaps millions of years, perhaps billions, however long it has been drifting through interstellar space, sailing through the cold dark between stars where sunlight is barely a whisper. But now there's heat. Gentle at first. The sun is still far away. But light is hitting this ancient object, and light carries energy. And energy, even a little bit, is enough to start something remarkable. The surface begins to warm, and when ice warms, even just a little, it doesn't melt, not in the vacuum of space. Instead, it sublimates. It transitions directly from solid to gas, skipping the liquid phase entirely. Water molecules that have been locked in crystalline structures for eons suddenly gain enough energy to break free. They lift off from the surface and drift into space, carrying dust particles with them. This is what we call activity. This is what makes a comet, rather than just a dark, inert rock. The sublimation of ice creates a cloud of gas and dust around the nucleus, the coma. And if the comet is active enough, if it's releasing enough material, that coma can grow large enough to see, even from millions of kilometers away. 3I Atlas is active, wonderfully, beautifully active. Observations from Earth-based telescopes have confirmed it. As the object approaches the sun, it's releasing gas. Spectroscopic measurements, careful analysis of the light reflected and emitted by the coma, tell us what molecules are present. Water vapor, certainly. Probably carbon dioxide, likely carbon monoxide, all the usual suspects we see in comets. But here's what makes this special. These molecules aren't from our solar system. They formed around another star, in another protoplanetary disk, under conditions that might have been subtly different from what happened here. The ratios of isotopes might be different. The mix of molecules might be different. The way they're organized in the ice matrix might be different. By watching 3I Atlas sublimate, by analyzing the gas and dust it releases, we're essentially sampling material from another stellar system. We're studying another star's planetary nursery without leaving home. It's as though the universe is running an experiment for us, taking a sample from over there and bringing it over here so we can compare. The process of sublimation is gentle. It's not an explosion or a violent release. It's more like breathing out on a cold day and watching your breath become visible. The ice warms just enough, molecules gain just enough energy, and they drift away, slowly, steadily, creating a growing cloud around the nucleus that catches sunlight and glows softly. This coma, this fuzzy atmosphere of gas and dust, can grow to be enormous, even though the nucleus itself is likely less than a kilometer across. We'll get to that. The coma can extend for thousands, or even tens of thousands of kilometers. It's like the object is wrapped in a soft, glowing blanket of its own making. And all of this is happening because of warmth. The same warmth that you might feel on your face when you step outside on a sunny day. Light carrying energy across space, touching an ancient traveler and waking it from its long, cold sleep. There's something almost alive about this process, isn't there? The comet was dormant, frozen, inactive. Then it enters a region with light and warmth, and it responds. It becomes active. It changes. It creates something new. This coma, this temporary atmosphere that will last only as long as the warmth does. Of course, it's not actually alive. It's just physics and chemistry, straightforward sublimation, molecular bonds breaking when given enough energy. But the metaphor is hard to resist. This ancient visitor, traveling through cold darkness for so long, finally enters a warm place and begins to, in a sense, wake up, to express itself, to show us what it's made of. The fact that we can observe this activity is a gift. It means the comet is close enough and bright enough to study. It means we can learn what molecules are present, how fast they're being released, how the activity varies as the comet's distance from the sun changes. Every observation adds to our understanding, and perhaps there's something comforting in knowing that even objects that have been cold and dark for billions of years can still respond to warmth. That given light and energy, they'll still sublimate, still release their frozen molecules, still create a glowing halo visible across space. The capacity for change, for activity, remains. Dormant perhaps, but not lost, just waiting for the right conditions. As sunlight warms it, frozen materials gently sublimate into a glowing halo. Ancient ice becomes gas. Silence becomes visibility. And we, watching from our small blue world, get to witness an awakening that has been billions of years in the making. Its coma, the fuzzy atmosphere around its core, appears reddish, hinting at long-aged, space-weathered dust. That soft red glow tells of billions of years drifting in cold interstellar darkness. Color tells stories. In astronomy, as in art, the specific hue of something can reveal its history, its composition, its journey. And 3I Atlas has a color worth noticing. Its coma glows with a subtle reddish tint, red, not dramatically red, not Mars red or blood red, more like a gentle blush, a warmth in the reflected sunlight, a soft glow that suggests something about the dust particles suspended in that growing cloud of gas. Why red? Well, that's where the story gets interesting. When astronomers see reddish coloring in comets or asteroids, they often think about something called space weathering. It's a process that happens slowly, very, very slowly, as objects drift through space. Cosmic rays hit them. Solar wind particles, when they're near a star, bombard their surfaces. Tiny micrometeorites impact them. Over time, these interactions change the surface materials at a molecular level. Specifically, they tend to create complex organic molecules, long chains of carbon, hydrogen, and other elements that absorb blue light preferentially and reflect more red light. It's a bit like how things rust on Earth, except instead of oxidation from oxygen, you have this gradual accumulation of radiation damage and chemical complexity. The process takes time, a lot of time. An object that's been in space for just a few million years might not show much reddening, but an object that's been drifting for hundreds of millions of years or billions of years, that object's surface dust will have had time to accumulate these changes, time to slowly transform into something that looks distinctly reddish to our telescopes. So when we see that 3I Atlas has a reddish coma, we're seeing evidence of age, deep cosmic age. We're seeing the visual signature of billions of years spent in the darkness between stars, where cosmic rays had ample time to work their slow magic on the dust particles. Think about what that means. The dust in that coma, those tiny particles being released as the ice sublimates, might have been sitting on the surface of this object since before our sun existed, before Earth formed, before any of the planets in our solar system had coalesced from their protoplanetary disk. This dust has been waiting, unchanged, for longer than our entire solar system has existed. And now it's glowing softly red in our telescopes, telling us about that immense span of time through its color. There's something poetic about the fact that age appears as a warmth, a reddish glow. You might expect ancient things to look cold, perhaps blue or white or colorless, but instead, time adds this gentle warmth to the appearance. The universe's way of showing its age is not through fading, but through a soft, ruddy complexion. Of course, red can mean other things too, the presence of certain organic molecules, for instance, or specific minerals. Scientists will carefully analyze the spectrum, not just whether it looks red, but exactly what wavelengths are being absorbed and reflected, to understand precisely what compounds are present. But that general reddish cast, that's the color of time. That's what happens when something has been exposed to the radiation environment of space for eons. It's a visual time stamp, readable from across millions of kilometers. When you think about it, we're looking at dust that has been stained by its journey. Every cosmic ray that struck it, every high-energy particle that collided with its molecules, left a tiny mark. Individually, those marks are invisible molecular scale changes, but collectively, over billions of years, they add up to something we can see, a subtle shift in color toward the red end of the spectrum. It's like looking at an old photograph that has yellowed with age, except on a cosmic scale. The yellowing of a photograph tells you it's old. The reddening of this coma tells you it's ancient. And there's a quiet beauty in that, isn't there? In the fact that age becomes visible, that time leaves traces, that something's journey through the cosmos is written, however subtly, in the wavelengths of light it reflects. 3I Atlas has been traveling a long time, longer than we can really comprehend, and that soft red glow is its way of showing us just how far it has come, how long it has been wandering, not through documents or records, but through the simple, elegant language of color. That red light falling on our telescopes has traveled across space, bounced off dust that has been space-weathered for billions of years, and arrived here to tell us, this visitor is old, truly, deeply old enough to have seen the galaxy change, old enough to have drifted past stars that have since died, old enough to carry the color of time itself. As you drift towards sleep, maybe you can picture it, that soft red glow in the darkness. Not harsh, not alarming. Just a gentle warmth, a blush of color against the black, telling a story of patient, endless wandering through the space between stars. The nucleus is likely less than a kilometer across, though precise size estimates remain uncertain. Measuring a distant, moving snowball across light years is a quiet triumph of precision. How do you measure something you can barely see? That's the central challenge with 3I Atlas. We know it's there. We can see the coma, that fuzzy cloud of gas and dust surrounding it. We can track its motion across the sky. We can analyze the light it reflects. But the actual nucleus, the solid core at the center of all that activity, that's much harder to pin down. The best estimates suggest it's less than a kilometer across, perhaps a few hundred meters, maybe as small as a few dozen meters. We're not entirely sure. And there's something both frustrating and wonderful about that uncertainty. Think about the scale of the challenge here. 3I Atlas, at its closest approach to Earth, is still millions upon millions of kilometers away. Trying to measure its nucleus is like trying to measure a pebble from across an entire continent. No, that's not quite right. It's more like trying to measure a grain of sand from across multiple continents. And that grain of sand is moving, and it's surrounded by a fuzzy cloud that obscures your view, and you have to do all this using only the light that bounces off it. When astronomers want to measure something this small and distant, they have a few techniques available. They can look at how bright it appears and make assumptions about how reflective the surface is. They can watch how quickly the brightness changes as it rotates, if it's rotating unevenly. They can, if they're very lucky, see it pass in front of a star and measure how long the star's light is blocked. They can analyze the coma to estimate how much material is being released and work backwards to guess at the nucleus size. But each of these methods comes with uncertainties, big uncertainties. The reflectivity of the surface, what astronomers call albedo, could vary widely. Is it dark like coal or bright like fresh ice? We don't know. The rotation rate? We're still working on that. The rate of gas production depends on how active it is, which can vary. So we end up with estimates, best guesses, ranges of possibility. Less than a kilometer across probably, but how much less? Could be 900 meters, could be 200, could be even smaller. And yet, there's something quietly magnificent about the fact that we can estimate it at all, that we can point our telescopes at a moving speck of light that formed around another star, that has been drifting through space for billions of years, that is now passing through our neighborhood for the briefest moment. And we can say, with some confidence, it's probably about this big. We live in an age where we can measure, with reasonable accuracy, objects that are smaller than many buildings, moving through space millions of kilometers away. That's astonishing. A few centuries ago, we didn't even know other stars existed. A few decades ago, we had never detected any interstellar visitors at all. And now? Now we can track them and measure them. The uncertainty in the measurement doesn't diminish the achievement. If anything, it highlights the difficulty of what we're attempting. Space is vast. These objects are tiny. Light takes minutes to travel from them to us. And somehow, using mathematics and careful observation and clever techniques, we can narrow down the possibilities. Less than a kilometer across, small enough to fit inside many city parks, small enough that you could walk around it in less than an hour if you could somehow visit it, but impossibly distant, moving at incredible speeds, surrounded by a coma that makes precise measurements challenging. It's a quiet triumph, as the saying goes, not flashy, not headline-grabbing, just careful, patient science working at the absolute edge of what's possible. People using telescopes and equations and computer models to extract tiny slivers of information from faint pinpricks of light. And maybe that's the right way to think about astronomy in general. It's not usually about dramatic revelations or sudden discoveries. More often, it's about slowly, carefully, patiently, gathering tiny pieces of information and assembling them into something approaching understanding. It's about measuring the immeasurable, one uncertain data point at a time. So yes, the nucleus of 3I Atlas is likely less than a kilometer across, we think, probably. The uncertainties are large, but they're narrowing. More observations will help. Better techniques will help. Maybe someday we'll know its size quite precisely. But for now, we have this. A reasonable estimate for a tiny object millions of kilometers away. A moving snowball from another star system, measured from afar. A small victory in humanity's long effort to understand the cosmos. One careful observation at a time. Sometimes the most impressive things are the quietest. Not the dramatic reveals, but the patient accumulation of knowledge. Not the certain answers, but the careful reduction of uncertainty. Not knowing everything, but knowing enough to keep asking better questions. Less than a kilometer, maybe, probably. And in that uncertain measurement lives the whole story of how we've learned to study the universe. Carefully, patiently, with humility in the face of vast distances and tiny signals. It contains volatile ices, such as water, carbon dioxide and carbon monoxide, preserved since before our sun formed. These frozen molecules are time capsules from another star's dawn. There's water inside 3I Atlas. Water ice, frozen solid, preserved for billions of years. The same substance that fills our oceans, that falls as rain, that we drink and cook with and use every day. Except this water formed somewhere else entirely, around a different star, in a different place, in a different time. When you really think about it, that's staggering. Every water molecule is simple. 2 hydrogen atoms bonded to 1 oxygen atom, H2O, the same structure whether it forms on Earth, in a cloud above Jupiter, or in a protoplanetary disk orbiting some distant star. Water is water, regardless of where it comes from. The chemistry is universal. But the individual molecules in 3I Atlas, they have a history. They formed when gas and dust collapsed under gravity to create a new solar system, not ours, but someone else's. They were incorporated into planetesimals, those small building blocks of planets. They were, at some point, ejected from that system, flung out by gravitational interactions. And they've been frozen ever since. How long? We don't know exactly, but likely for billions of years, possibly longer than our entire solar system has existed. These water molecules were solid ice before Earth had oceans, before Earth existed at all, before the sun lit up for the first time. They're time capsules in the most literal sense, frozen samples from another place and time, preserved by the perfect cold of interstellar space, and now delivered to us by chance and orbital mechanics. But it's not just water. Spectroscopic analysis has detected or suggested the presence of other volatile molecules. Carbon dioxide, the same gas we exhale that makes dry ice, that fills Mars's polar caps. Carbon monoxide, a simple molecule, just carbon and oxygen bonded together, poisonous to us but common in space. These molecules tell us about the conditions where 3I Atlas formed. The mix of molecules, and especially their ratios to each other, can reveal details about the temperature and composition of the disk where this object originated. Was it rich in carbon? How much oxygen was available? What was the temperature like at the distance where ices could condense? Each molecule is a clue. Scientists can compare these molecular ratios to what we see in comets from our own solar system. Are they similar? That might suggest that planetary formation follows similar patterns everywhere. Are they different? That tells us something about the diversity of stellar nurseries across the galaxy. Maybe some stars form with different chemical compositions. Maybe the processes vary depending on the mass of the forming star or the density of the surrounding cloud. Every measurement adds to our understanding, and every molecule in 3I Atlas's ice is a piece of data from a cosmic laboratory we can never visit. Think about the preservation here. For these ices to survive billions of years, they had to stay cold, very cold, away from stars, away from significant sources of heat. If 3I Atlas had passed close to another star at any point in its long journey, the warmth would have sublimated the ice. The molecules would have been released into space, lost forever. But that didn't happen. This object stayed in the cold, dark spaces between stars, maintaining its frozen cargo, until now. Now it's passing close to our sun, and those ancient molecules are finally being released. Water vapor is lifting off the surface. Carbon dioxide is sublimating. The time capsule is opening, slowly, gently, as heat touches it, for perhaps the first time in billions of years. It's like finding a message in a bottle, except the bottle took eons to arrive, and the message is written in the language of chemistry rather than words. Each molecule that sublimates from 3I Atlas's surface carries information about where it came from, encoded in its isotopic ratios and its bonding patterns and its behavior in sunlight. We're reading that message now as best we can. Telescopes are analyzing the light, looking for the spectral signatures of different molecules. Scientists are comparing the data to models and to measurements of our own comets. Slowly, carefully, we're learning what this visitor is made of. And what we're learning is that, in many ways, it's not so different from our own comets. Water, carbon dioxide, carbon monoxide, These are common molecules in protoplanetary disks. The chemistry that produces them seems to be fairly universal, which is, in its own way, comforting. It suggests that the processes that formed our solar system aren't unique. Other stars form the same way. Other protoplanetary disks have similar compositions. Other planetary systems might look, at least chemically, somewhat like ours, but there might be differences too. Subtle differences in ratios, in isotopes, in the presence of trace molecules. And those differences are equally important because they tell us about the diversity of the galaxy, about how conditions vary from one stellar nursery to another. So as you settle into sleep, imagine molecules of water, of carbon dioxide, of carbon monoxide, frozen for longer than you can truly comprehend, now warming in sunlight, sublimating, drifting into space, time capsules opening, messages from another star's dawn, finally being read after a journey measured in billions of years and trillions of kilometers. The ices are sublimating, the time capsules are opening, and we briefly get to peek inside and see what they contain. Nickel vapor has been detected in its gas cloud, a surprising clue to its complex chemistry. Metallic vapors like nickel whisper of ancient, exotic processes in its birthplace. Nickel. Not quite what you'd expect to find sublimating from a comet's surface, is it? When we think about comets, we usually think about ice. Water ice, primarily, along with frozen carbon dioxide, frozen carbon monoxide, maybe some frozen methane or ammonia. These are the volatiles, the substances that sublimate easily when warmed by sunlight. They're what create the coma and the tail, the visible features that make a comet a comet. Metals, on the other hand? Metals are refractory materials. They have high melting and boiling points. They should stay locked in the solid nucleus, far too stubborn to sublimate at the gentle warmth of sunlight, even fairly close to the sun. And yet, nickel vapor has been detected in 3I Atlas's coma. Along with it, likely other metallic vapors like iron and magnesium, though nickel is particularly notable because it's a bit more unusual. How did it get there? That's the puzzle. And like many puzzles in astronomy, there are several possible answers, and we're not entirely certain which is correct. Maybe it's all of them working together. One possibility is that nickel atoms are trapped in the ice matrix. When the ice sublimates, it releases not just water molecules, but also tiny dust grains and embedded atoms. The nickel might be hitchhiking, essentially, carried along by the sublimating ice. This happens with our own comet sometimes. As ice sublimates, it drags along materials that wouldn't normally sublimate on their own. Another possibility involves the dust grains themselves. Cometary dust often contains tiny metallic particles, remnants of the material that existed in the protoplanetary disk before planets formed. When these dust grains are released into the coma, they're exposed to intense ultraviolet light from the sun. That UV light can be energetic enough to break chemical bonds, liberating metal atoms from minerals and causing them to vaporize. It's called photodissociation or photosputtering, and it can release metal vapors even when the temperature isn't high enough to melt or boil the metals normally. There's also the possibility that the nucleus has some unusual composition or structure. Maybe there are regions rich in metallic compounds that sublimate more easily than pure metals. Maybe the object's formation process was different from typical solar system comets. incorporating metals in ways we don't usually see here. Whatever the mechanism, the presence of nickel vapor tells us something important. This object has a complex chemistry. It's not just a simple ball of ice. It contains metals, minerals, complex organic compounds, all mixed together in ways that reflect its formation history. Nickel specifically is interesting because it's often associated with differentiated bodies, objects that have been heated enough to separate into layers, with metals sinking toward the center. Large asteroids sometimes have metallic cores, rich in iron and nickel. But 3I Atlas is a comet, not an asteroid. It shouldn't have been heated enough to differentiate. So where did the nickel come from? Perhaps it was present in the original dust of the protoplanetary disk, where 3I Atlas formed. Perhaps that disk had a different composition than ours, richer in certain metals. Perhaps the star it formed around had a different chemical makeup, having formed from gas clouds with different abundances of elements. You see, stars are not all identical. Older stars, formed earlier in the galaxy's history, have fewer heavy elements, less carbon, less oxygen, less iron, less nickel. Younger stars, formed from gas clouds, enriched by previous generations of stars that exploded as supernovae, have more of these heavy elements. The exact ratios vary, depending on the star's history and location in the galaxy. So the nickel in 3I Atlas might be telling us something about the star it formed around. Maybe that star was particularly rich in metals. Maybe it formed in a region of the galaxy where supernova enrichment was especially strong. Maybe the protoplanetary disk had a composition we don't commonly see in our own solar system. These are whispers, not shouts, clues, not answers, but they're fascinating clues. Every metal vapor detected, every molecule identified, every spectral line measured adds to our understanding of how diverse the galaxy really is. How many variations exist on the theme of planetary system formation? How much we still have to learn. And there's something almost poetic about metallic vapors sublimating from ancient ice. Metals that formed in a star that exploded long before our sun existed, incorporated into a comet that has been wandering the galaxy for billions of years, now vaporizing in our sunlight and glowing faintly in our telescopes. It's a connection across time and space, written in the language of nickel vapor and spectroscopic measurements. These metallic vapors, like nickel, don't scream for attention. They whisper. They hint at exotic processes, ancient environments, chemical compositions that differ from what we're used to. They invite curiosity without demanding answers. They remind us that even something as seemingly simple as a comet can hide layers of complexity, stories written in its chemistry, waiting to be read. As you drift deeper toward sleep, maybe let that image settle in your mind. Ancient metals formed in exploding stars, incorporated into ice around a different sun, carried across the galaxy for billions of years, now vaporizing softly in our skies, whispers from elsewhere, hints of processes we're only beginning to understand, a metallic surprise in a cosmic visitor, glowing faintly against the dark. As it nears the sun, 3I Atlas has developed a visible jet aimed sunward, venting material into space. Solar warmth awakens its icy surface, creating a graceful fountain of light. Not all of 3I Atlas is warming evenly. The sun's light hits different parts of its surface at different angles, at different intensities. Some regions heat up more than others. Some patches of ice begin sublimating faster. and in at least one location, the activity has become focused, concentrated into what astronomers call a jet. Imagine it, a narrow stream of gas and dust erupting from the nucleus, shooting out into space like a fountain, not randomly in all directions, but focused, directional, a visible jet of material venting into the vacuum. And here's what makes it particularly interesting. This jet appears to be aimed sunward, toward the sun, which makes sense when you think about the physics. The side facing the sun is the side receiving the most heat, so that's where you'd expect the most vigorous sublimation. But it's still striking to imagine this ancient visitor approaching our sun, developing a fountain of light aimed directly at the source of warmth. Jets are common in active comets. They're not unusual, but each jet tells a story about the comet's surface, about where the ice is most accessible, about how the object is rotating, about the geology, or perhaps we should say cometology, of its nucleus. When ice sublimates from a jet, it carries dust with it. The gas molecules lift off, and the drag forces pull along tiny dust particles. These particles are too small to see individually, but collectively they scatter sunlight, creating a visible stream. In photographs, jets often appear as bright rays emanating from the coma, sometimes curved gracefully by the comet's rotation and by the pressure of sunlight and solar wind. The jet on 3I Atlas is a sign of active, dynamic sublimation. It's not just gently releasing gas uniformly across its surface, it's venting. Specific regions are more active than others, creating this directional flow. Why would one region be more active? There are several possibilities. Perhaps that part of the surface has a thinner layer of dust covering the ice, allowing sunlight to penetrate more effectively. Perhaps there's a crack or fissure in the nucleus where ice is more exposed. Perhaps the ice in that region has a different composition, more volatiles, more easily sublimated materials. Or perhaps it's simply the geometry of rotation. As the nucleus tumbles through space, different regions cycle through periods of sunlight and shadow. When a patch of ice that's been in shadow suddenly rotates into sunlight, it can begin sublimating vigorously, creating a temporary jet. Then, as rotation continues and that patch moves back into shadow, the jet fades, and a different region becomes active. It's a dance, really, a slow rotation measured in hours or days, with different faces of the nucleus taking turns in the sun's warmth, and with each turn, jets appear, evolve, and fade, creating an ever-changing pattern of activity. The fact that we can observe this jet, that we can see this structure in the coma, tells us that 3I Atlas is relatively active. Not all comets develop visible jets. Some just have diffuse, uniform comas without much structure. But this visitor, it's putting on a show, and calling it a fountain of light isn't just poetic license. The sublimating gas and dust really do catch sunlight and glow. Not with their own light, they're not burning or incandescent, but reflected and scattered sunlight makes them visible, creates this luminous stream arcing out from the nucleus. Picture it in your mind, a small, dark nucleus, perhaps tumbling slowly, with one side facing the sun. From that sunward face, a stream of gas and dust erupts continuously, flowing outward at hundreds of meters per second. Sunlight catches the dust particles, making the jet glow against the black of space. The gas, though mostly invisible, carries the dust along, creating this graceful arc. It's gentle, despite the speeds involved. Not explosive, not violent, just steady sublimation, molecules gaining enough energy to escape, lifting dust along with them, creating this fountain that flows continuously as long as that particular region remains in sunlight. And this is happening right now, as 3I Atlas makes its close approach to the sun. Solar warmth is awakening its icy surface in real time. Molecules that have been frozen for billions of years are finally, gently, lifting into space. Ancient material from another star system is sublimating in our sun's light, creating a visible jet that astronomers on Earth can photograph and study. There's something beautiful about that timing. For all the billions of years this object has been wandering through cold space, it's happening to be near the sun right now, right when we're here to observe it, right when we have the technology to study it. A coincidence of timing that lets us witness this ancient ice finally warming, finally becoming active, finally creating this graceful fountain of light. The jet won't last forever. As 3I Atlas completes its swing around the sun and begins moving back out into the cold reaches of space, the warmth will fade. The sublimation will slow. The jet will weaken and eventually disappear. The coma will shrink and fade, and the object will return to its dormant state, cold, dark, inactive, as it sails back into the vast spaces between stars. But for now, for this brief moment in its billion-year journey, it's active, it's venting, it's creating a fountain aimed sunward, a visible sign of ancient ice meeting stellar warmth. Solar warmth awakening its icy surface, creating something graceful and fleeting and beautiful, a fountain of light flowing from a visitor from another star, catching the sun's glow and showing us, for just a little while, that it's here, that it's active, that it's responding to warmth after eons of cold. The object poses no threat to Earth. Its path keeps it safely distant from our planet. We can watch its passage in peace, a cosmic visitor, not a danger. Let's take a moment for reassurance, because this matters. Whenever we talk about objects from space, about comets passing through our solar system, there's sometimes an undercurrent of worry. Movies and sensational headlines have trained us to think of incoming objects as potential threats, harbingers of catastrophe. But 3I Atlas? It's not a danger, not to Earth, not to anything in our solar system. Its orbit has been calculated precisely, and those calculations show clearly that it's not going to hit us. It's not even going to come particularly close. Its path through the solar system is a gentle curve, approaching from one direction, bending around the sun due to gravity, and departing in another direction. At no point does that path intersect with Earth's orbit in any threatening way. The distances involved are measured in astronomical units. The distance from Earth to the sun is 1 AU, and 3I Atlas stays well away from that distance in its passage through our neighborhood. This is worth emphasizing because fear robs us of wonder. When we're worried about something, we can't fully appreciate it. We can't settle into the calm contemplation that makes astronomy so soothing, so conducive to rest and reflection. So let me be clear. You can watch this visitor in peace. You can read about it, think about it, let your mind wander through the facts about it without any anxiety. It's a cosmic visitor, not a danger, a messenger, not a threat, something to wonder about, not worry about. The astronomers who discovered it and who continue to track it are certain about this. They've calculated its trajectory with high precision. They know where it came from, where it's going, and where it is at every moment. And none of those calculations suggest any risk to our planet. In fact, one of the reasons we're able to study 3I Atlas so thoroughly is precisely because it's on a safe trajectory. If it were approaching Earth closely, much of our attention would necessarily focus on determining whether it poses a risk, and, if so, what to do about it. But because we know it's safe, we can relax and simply observe, simply learn, simply appreciate this rare opportunity to study an interstellar visitor up close. The same was true for 1I Oumuamua and 2I Borisov. Both of those interstellar visitors passed through safely, posing no threat to Earth. They were scientific opportunities, not dangers. And 3I Atlas is following that same pattern. Interesting, valuable, and completely safe. There's something almost gentle about that. The universe, for all its violence and chaos, for all its colliding galaxies and exploding stars, sometimes just sends us quiet visitors, objects that pass through peacefully, that we can study without concern, that offer knowledge without risk. Perhaps that's part of what makes these interstellar visitors so special. They're not asteroid impact scenarios requiring emergency response teams. They're not existential threats demanding urgent action. They're just visitors, travelers from far away, passing through our neighborhood on their way to somewhere else, and kind enough, if we can anthropomorphize for a moment, to stay at a safe distance. You can picture it like a ship passing at sea. It's visible on the horizon. You can watch it through binoculars or a telescope. You can wonder about where it came from and where it's going. But it's not on a collision course. It's just passing by, and you can watch its passage with curiosity and peace, not fear and alarm. This is the state of mind conducive to truly appreciating astronomy. When we know we're safe, when we know we can simply observe and learn without worrying about consequences, we can let our minds expand into the vastness of space. We can contemplate billions of years and trillions of kilometers without anxiety. We can think about the age and scale and complexity of the universe from a place of calm wonder. And that's good for sleep too. Anxiety keeps us awake. Wonder, contemplative wonder without urgency or fear, helps us rest. It's the difference between being chased by a tiger, activating our stress responses, keeping us vigilant, and watching clouds drift by, engaging our curiosity while allowing our bodies to relax. 3I Atlas is clouds drifting by. It's a ship on the horizon. It's a visitor passing through at a safe distance. We can watch its passage in peace. The calculations that confirm this safety are themselves a kind of marvel. Astronomers can track this object's position across multiple nights, note how it moves against the background stars, and from those observations alone, calculate its entire orbital trajectory. They can determine where it was weeks ago, where it is right now, and where it will be months from now. They can project its path forward and backward in time, understanding its journey through the solar system with remarkable precision. And all of those calculations agree. It poses no threat. Its path, while carrying it through our cosmic neighborhood, keeps it comfortably distant from Earth. We're spectators, not targets. Observers, not participants in any close encounter. So rest easy. Let your shoulders relax. Release any unconscious tension you might have been holding. This ancient visitor from another star system is interesting, remarkable, worthy of contemplation. But it's not dangerous. Not to you, not to Earth, not to anyone. We can watch its passage in peace, We can study it, learn from it, appreciate it. We can let our minds wander through the facts of its journey without any anxiety about where that journey might lead. It's a cosmic visitor, bringing us information and wonder from beyond our solar system, and it's doing so safely, at a distance, following the mathematical curves of gravity with perfect predictability. It entered the solar system from the southern celestial hemisphere, near the Milky Way's central region. Its unexpected arrival direction reminds us how vast and unsurveyed our skies remain. When astronomers first calculated 3I Atlas's trajectory, working backward from its observed motion to determine where it came from, they found something interesting. It entered our solar system from the south, from the southern celestial hemisphere, to be more precise, from a region of sky that lies in the general direction of the Milky Way center. Why is that interesting? Well, in part because we didn't expect it from that direction. Not that we had specific expectations, exactly. It's not like we predicted an interstellar visitor would arrive from the north and were surprised when it came from the south. But we do have biases in what we can see. Most of our major telescopes are in the northern hemisphere, simply because most humans live in the northern hemisphere, and that's where we've built most of our observatories. We survey the northern skies more thoroughly than the southern skies. So when an object arrives from the south, there's a chance we might miss it, or catch it later than we would if it had come from the north. The fact that Atlas, the telescope in Chile, one of the relatively few major survey systems in the southern hemisphere, caught 3I Atlas is a bit fortunate. If it had passed through a few years earlier, before Atlas was fully operational, we might have missed it entirely. But beyond the practical aspects of northern versus southern skies, there's something philosophically interesting about the direction. 3I Atlas came from the general direction of the Milky Way's center. That's where most of our galaxy's stars are concentrated. That's where the density of stars is highest. That's where, statistically speaking, most interstellar objects probably originate. But general direction is doing a lot of work in that sentence. The Milky Way's center is about 26,000 light-years away. 3I Atlas almost certainly didn't come directly from the center. It probably originated from some star system somewhere in that general direction. But which star? We don't know. We may never know. Space is big, really big. And trying to trace 3I Atlas's path backward to a specific star of origin is extraordinarily difficult. As it traveled through interstellar space, it was subtly deflected by the gravity of other stars it passed. Each deflection was small, but over billions of years and trillions of kilometers, they add up. The path curves and bends in ways that become impossible to reconstruct precisely. So we know it came from the south, from somewhere in the direction of the galactic center. But more specifically than that, the trail goes cold, lost in billions of years of gravitational interactions and unknowable deflections. And there's something humbling about that. We can track this object's motion through our solar system with extraordinary precision. We can predict where it will be months from now, but we can't tell you which star it came from, can't identify its birthplace, can't point to a specific point of origin and say, there, that's home. The unexpected arrival direction reminds us how vast and unsurveyed our skies remain. We like to think we're watching the heavens carefully, that we've got a good handle on what's out there. And in many ways, we do. We've mapped millions of stars, cataloged countless galaxies, tracked thousands of asteroids. But interstellar space, the space between stars, that's barely surveyed at all. We catch glimpses when objects pass through our immediate neighborhood, but the vast majority of what's drifting through that emptiness remains invisible to us. Too far away, too dark, too small. Moving through regions we're simply not watching. It's like having a detailed map of your own house and the immediate street outside, but having almost no information about the country beyond. You know your neighborhood well, but the wider world? That's mostly unknown. 3i Atlas appeared from that unknown, from a direction we weren't particularly focused on, from a region of space we can't monitor continuously, carrying a history we can't fully reconstruct. And perhaps that's okay. Perhaps mystery is part of the gift. If we knew everything about where it came from, if we could trace its entire billion-year journey from birth to now, would it be as wonder-inducing? Or is some of the wonder precisely in the unknowing, in the fact that it arrived unexpectedly from the south, from somewhere out there in the vast dark? The southern celestial hemisphere, when viewed from most human population centers, is less familiar. It contains different constellations, different patterns of stars. For people in the northern hemisphere, the southern sky is foreign territory, rarely seen or never seen at all, depending on latitude. So 3i Atlas arrived from unfamiliar territory, from a part of the sky that's less watched, less studied, less known to most of us. It came from the direction of mystery, bringing mysteries with it. Its unexpected arrival direction doesn't change anything about the object itself. It's still the same ancient visitor, carrying the same frozen molecules, releasing the same gases. But it reminds us of our limitations, of how much we don't see, of how many visitors might be passing through without our noticing. The skies are vast, our surveys are improving, but they're still incomplete. Objects can still surprise us by arriving from directions we weren't watching as carefully. The universe still has the capacity to send messengers we almost miss. And maybe, as you drift toward sleep, there's something comforting in that. In knowing that the universe still has surprises, that the skies remain vast and partially unsurveyed, that despite all our telescopes and all our careful watching, mystery remains. Travelers can still arrive unexpectedly from the south, from the general direction of the galactic center, from somewhere out there we can't quite pinpoint. How vast and unsurveyed our skies remain. How much is passing through that we never notice. How fortunate we are then, when we do catch a glimpse of these wanderers, when a telescope happens to be watching the right patch of sky at the right moment, when an unexpected visitor from the south enters our awareness, if only briefly. 3i Atlas may be older than our solar system, perhaps over 5 billion years old. It may have formed when our galaxy was still settling into its current shape. Let's think about age for a moment. Deep, cosmic age. The kind of age that makes human lifespans seem like brief flickers. Our solar system is about 4.6 billion years old. That's the age of the sun, the age of Earth, roughly the age of all the planets. Everything in our cosmic neighborhood formed around the same time, from the same cloud of gas and dust, about 4.6 billion years ago. But 3i Atlas, it might be older than that, significantly older, perhaps over 5 billion years old, maybe even older still. We can't know this with certainty, of course. We don't have a birth certificate for this object. We can't carbon date it? Well, we could in principle, but we'd need a sample, and we're not going to get one. What we have are estimates based on its characteristics, its composition, and what we understand about when and where such objects form. If it's over 5 billion years old, that means it formed before our solar system existed, before the sun ignited, before Earth was anything more than a diffuse cloud of gas and dust, before the planets coalesced, before any of the familiar landmarks of our cosmic home came into being. Try to hold that in your mind. This small icy object has been wandering through space since before our sun was born. When 3I Atlas formed, perhaps around some other star in some other part of the galaxy, our solar system didn't exist yet. The gas cloud that would eventually collapse to form the sun and planets was still just gas, dispersed, undistinguished, not particularly special, just another cloud among countless clouds in the galaxy. And while that gas was slowly beginning to collapse under its own gravity, a process that would take millions of years, 3I Atlas was already out there, already formed, already wandering, a complete object while our entire solar system was still just potential. 5 billion years. It's hard to really grasp that time span. Human civilization is perhaps 10,000 years old. Homo sapiens as a species is perhaps 300,000 years old. The dinosaurs went extinct 66 million years ago. Earth itself is 4.6 billion years old. And 3I Atlas might be older than all of it, except the dinosaur extinction. This object has been traveling through space for longer than our planet has existed. Every atom in your body, every molecule of water you've ever drunk, every breath of air you've ever breathed, none of it existed when 3I Atlas was already out there, already wandering between stars. The galaxy itself was different then. 5 billion years ago, the Milky Way was still settling into its current spiral structure. Stars that have since lived their entire lives and died weren't born yet. The sun, which now seems eternal and unchanging from our human perspective, didn't exist. And through all of that change, through all of that time, 3I Atlas has been traveling, not conscious, not aware, just following the mathematics of gravity and momentum, drifting through interstellar space at speeds we can barely imagine, sustained for durations we can barely comprehend. It may have passed by stars that have since exploded as supernovae. It may have drifted through regions of space where new stars were forming, where protoplanetary disks were coalescing into planets. It may have witnessed, if we can use that word for an inert object, the birth and death of stellar systems across a significant fraction of our galaxy's volume. And now it's here, passing through a solar system that didn't exist when it began its journey, being observed by creatures on a planet that formed billions of years after it was ejected from its home system. There's something almost melancholic about that. This ancient wanderer, older than our sun, finally arrives in our neighborhood only to pass through and leave. We get this brief moment to observe it, to study it, to wonder about it. But it's been traveling since before we were even possible, and it will continue traveling long after we're gone. Or perhaps it's not melancholic. Perhaps it's simply what the galaxy does. Objects form. They get ejected. They wander for incomprehensible spans of time. Occasionally, they pass through younger solar systems where observers happen to exist. Then they continue on. The age of 3I Atlas, if our estimates are right, tells us something important about the longevity of these objects. Ice can survive in space for billions of years. The cold preserves it. The vacuum protects it. An object can maintain its integrity, can carry its cargo of frozen molecules for spans of time longer than the age of our entire solar system. That's a kind of immortality, in a sense. Not life, certainly, but persistence, endurance, the ability to exist, unchanged in any fundamental way, for timescales that dwarf civilizations, species, even worlds. As you drift toward sleep, let that age settle in your mind. Over 5 billion years, older than the sun, older than Earth, formed when our galaxy was still settling into its current shape. And now, finally, briefly, passing through our neighborhood. All that time, all that distance, all that patient wandering through the dark. And for just this moment, it's here, visible in our telescopes, a visitor from the ancient past of our galaxy carrying ice that formed before our solar system existed, releasing gases that have been frozen since before Earth was born. It may be older than our solar system, perhaps over 5 billion years old, a wanderer from the galaxy's ancient past, finally arriving in our young solar system's neighborhood, briefly visible, soon to leave, carrying its age like a quiet dignity, like a story too long to ever fully tell. Astronomers believe it was ejected from another star system's protoplanetary disk by gravitational nudges. Flung free long ago, it became a wanderer between suns. Every wanderer has an origin story. Every traveler was somewhere once before they began traveling. And for 3I Atlas, that origin was almost certainly within another star system, a solar system not unlike ours, but far away and long ago. Picture it, billions of years ago in some other part of the galaxy, a cloud of gas and dust collapsed under its own gravity. The center of that cloud became denser and denser, heating up until nuclear fusion ignited, and a new star was born. Around that star, the remaining gas and dust formed a disk, a protoplanetary disk, we call it now, the structure from which planets eventually form. Within that disk, small objects began to coalesce. Dust particles stuck together through electrostatic forces. Small clumps collided and merged, growing larger. These objects, planetesimals, we call them, are the building blocks of planets. Most of them eventually collide with each other and merge, gradually building up the handful of large planets that will orbit the new star. But not all of them. Some planetesimals remain small, some are unlucky, and some, like the object we now call 3I Atlas, get ejected entirely. How does ejection happen? Through gravitational interactions. As planets begin to grow large, they exert significant gravitational influence on everything nearby. A small object passing close to a massive forming planet can receive what's called a gravitational slingshot. Its trajectory bends sharply, and it can gain or lose velocity dramatically. Most often these interactions just change an object's orbit within the system. But sometimes, rarely, the nudge is strong enough to fling the object completely out of the system. The planetesimal reaches escape velocity, the speed necessary to overcome the star's gravitational pull, and sails away into interstellar space. It's a form of exile. Not intentional, of course. Gravity doesn't have intentions, but the effect is the same. The object is flung free, leaving behind the star system where it formed, setting out on an indefinite journey through the space between stars. This might sound violent, but it's not really. It's just mathematics. just the inevitable consequences of many objects with mass interacting gravitationally in a confined space. In any forming planetary system, some fraction of the material gets ejected. It's a normal part of the process. Our own solar system likely ejected countless objects during its formation. Some of them are probably still out there, wandering through the galaxy, carrying ice and dust from our protoplanetary disk to distant regions of space. Maybe billions of years from now, one of them will pass through another star system, and observers there will study it and wonder about its origin. 3I Atlas underwent this process somewhere else. It formed in another system, accumulated its ice and rock in another protoplanetary disk, and then, through bad luck, through wrong place at wrong time, through the complex dance of gravitational interactions, it was flung free. How long ago? We don't know precisely, but given its age, possibly over 5 billion years, the ejection likely happened very early in that system's history. Shortly after the planets began forming, when gravitational interactions were most chaotic and energetic. Since then, it has been wandering, not orbiting anything, not bound to any star, just moving through space, following the trajectory imparted by that ancient gravitational nudge, influenced only by the gentle gravitational tug of the galaxy itself, and by occasional distant encounters with other stars. It's been moving through interstellar space for billions of years, through regions of space where stars are sparse and darkness is nearly absolute, occasionally passing relatively near other stars, though near, in galactic terms, might still mean trillions of kilometers. Slowly moving through the spiral arms of the galaxy, following a path that's curved and complex when viewed on galactic scales, but essentially straight when viewed locally. And then, finally, after all that time, it happened to pass through our solar system, not because it was aimed here, not because of any special destination, just because orbital mechanics and billions of years of motion happened to carry it through this particular region of space at this particular time. It's chance, cosmic chance. The same gravitational interactions that ejected it from its birth system eventually brought it, billions of years later, to ours. There's no message in that, no meaning or purpose. It's just physics playing out over incomprehensible timescales. But there's a kind of poetry in it nonetheless. This object was exiled, flung free from its home, and has been wandering ever since. And we, orbiting a younger star in a different part of the galaxy, get to see it pass through. Get to briefly observe this ancient wanderer and wonder about its long, lonely journey. Flung free long ago, it became a wanderer between suns, not orbiting, not bound, not belonging to any particular star system, just traveling through the galaxy's vast spaces, maintaining its trajectory, carrying its frozen cargo of ancient ice, occasionally passing close enough to a star to briefly warm and sublimate before moving on. It's solitary, in a sense, but perhaps not lonely. Loneliness requires consciousness, and 3I Atlas is just matter, following laws of physics. Still, the image is evocative, a wanderer between suns, an exile, an object that was once part of a system, part of the chaotic process of planet formation, and then was cast out to travel indefinitely. And maybe, as you drift toward sleep, you can imagine that long journey. The initial fling outward, accelerating past the escape velocity, leaving the light of its birth star behind. the gradual cooling as it moves into interstellar space, far from any warming light. The billions of years of silent drift through darkness, moving ever onward, following the path carved by that ancient gravitational nudge. Astronomers believe it was ejected from another star system's protoplanetary disk by gravitational nudges. Past tense. It happened long ago, and the consequence, the wandering, the billion-year journey, the passage through our system, is still unfolding, still playing out. The exile continues. But for this brief moment, we can see it. We can study it. We can acknowledge this wanderer and its impossibly long journey. And then, as it must, it will continue on, between suns, into the dark, carrying its ancient ice to whatever regions of space lie ahead in its eternal drift. Studying it gives us a natural sample of material from beyond our solar system. It's as though the galaxy itself sent us a fragment of its wider story. There's something almost generous about 3I Atlas when you think about it in a certain light. We can't travel to other star systems, not with current technology, not in any human lifetime that we can imagine. The nearest star system, Alpha Centauri, is over 4 light years away, so distant that even traveling at extraordinary speeds, a journey there would take decades or centuries. We're confined for now to our own solar system. We can study the sun, the planets, the moons, the asteroids and comets that share our cosmic neighborhood. We've learned an enormous amount from these local objects, but they all formed together from the same cloud of gas and dust about 4.6 billion years ago. They're all part of the same family, genetically speaking. Same basic composition, same formation history, same cosmic origin story. If we want to understand how other solar systems form, how planetary systems in different parts of the galaxy might differ from ours, we need samples from elsewhere. We need to study material that formed under different conditions, around different stars, in different environments. And we can't go get it. We can't send a spacecraft to another star system and return with samples. The distances are too vast, the timescales too long, the energy requirements too extreme. So the universe has to come to us, and occasionally, wonderfully, it does. 3I Atlas is a delivery, a natural sample of material from beyond our solar system, delivered right to our neighborhood, ready to be studied with our telescopes and instruments. We didn't have to go anywhere. We didn't have to build impossible spacecraft or wait centuries for data to return. The galaxy itself sent us a fragment of its wider story. It's not a controlled sample, of course. We didn't get to choose which star system it came from, or what kind of protoplanetary disk environment it formed in, or what specific materials it contains. We get what we get, but that's okay. Any sample from beyond our solar system is precious. Any data point from a different stellar environment adds to our understanding. By studying 3I Atlas, its composition, its behavior, its chemistry, we're learning about processes that happened elsewhere in the galaxy. We're seeing what kinds of ices form in other protoplanetary disks. We're measuring isotopic ratios that reflect the chemical makeup of other stellar nurseries. We're observing how comets from other systems respond to sunlight, and how that might differ from our own comets. It's comparative astronomy, like a biologist studying plants from different ecosystems to understand which features are universal and which are environment-specific. Astronomers can study 3I Atlas alongside solar system comets to understand what's universal about comet formation and what varies from system to system. Every measurement matters. Every spectral line captured, every photometric observation logged, every chemical analysis completed. All of it is data we couldn't obtain any other way. We're building a picture of what exists beyond our immediate neighborhood, one interstellar visitor at a time. With 3 confirmed interstellar objects now, Oumuamua, Borisov, and Atlas, we're starting to see patterns and variations. Oumuamua was strange, possibly a comet that had lost its volatiles or something we didn't quite understand. Borisov looked like a fairly normal comet, similar in many ways to our own. And Atlas is showing us yet another variation, a comet with metallic vapors in its coma, with a reddish hue suggesting ancient space weathering, with active jets and familiar ices. Each one is a data point. Each one tells us something about the diversity of objects wandering the galaxy. Each one is a fragment of the galaxy's wider story, delivered to us naturally, without requiring any impossible feats of space travel. And perhaps that's the right way to think about it. The galaxy has been forming stars and planets for billions of years. Countless solar systems have gone through the same basic process. Gas cloud collapses, star ignites, protoplanetary disk forms, planets coalesce, some material gets ejected. This has happened over and over and over across the galaxy's history. And all that ejected material, all those planetesimals flung free from their birth systems, are out there now, wandering. Billions of them probably, trillions perhaps, all carrying samples from their respective stellar nurseries, all drifting through the dark, all following the complex gravitational dance of the galaxy. Occasionally, one of them passes through another solar system, through our solar system, and when it does, we get a glimpse of somewhere else. We get to study material that formed in conditions we can never directly observe. We get a natural sample delivered by chance and orbital mechanics, ready to teach us about the wider galaxy we inhabit. It's as though the galaxy itself sent us a fragment of its wider story. Not intentionally, of course. The galaxy doesn't have intentions, but the metaphor is apt. Through the natural processes of planetary system formation and gravitational ejection, the galaxy is constantly distributing samples of itself. Most of them drift unseen through empty space, but a very few, happen to pass through systems where observers exist and notice them. We're those observers. And 3I Atlas is our sample, a fragment of galactic history, a piece of someone else's stellar neighborhood, a messenger carrying information about conditions elsewhere in space and time. We didn't have to leave home to study it. We just had to watch carefully. Just had to have our telescopes pointed in the right direction at the right time. Just had to be ready to recognize something unusual when it appeared. And now we're learning from it, extracting information from its light, from its motion, from its chemistry, building up our understanding of how the galaxy works, one natural sample at a time. It's efficient in a way. The galaxy does the hard work of delivering samples. We just have to be ready to receive them and study them. And with improving telescope networks and better survey systems, we're getting better at catching these visitors. What once seemed impossibly rare, an interstellar object passing through, is becoming, if not common, at least occasionally expected. Maybe in a few decades, We'll have cataloged dozens of interstellar visitors, maybe hundreds, each one a natural sample, each one a fragment of the galaxy's wider story, each one teaching us something about the diversity of stellar environments and planetary formation processes across our galactic neighborhood. But for now, we have 3. And the third one, 3I Atlas, is here right now, sublimating in our sun's warmth, releasing ancient molecules for us to study, giving us a glimpse of material from beyond our solar system. A natural sample, delivered by the galaxy, studied by human observers, adding to our knowledge, one ancient ice crystal at a time. It's as though the galaxy itself sent us a fragment of its wider story, and we're reading that fragment as carefully as we can, extracting every bit of meaning, every piece of information, every clue about the wider universe we inhabit, but can only partially see. Its chemistry and behavior may differ subtly from local comets, offering a rare point of comparison. By contrasting it with solar system comets, we glimpse other ways planets might form. We've studied comets for a long time. Centuries, really, if you count the early observations of bright comets visible to the naked eye. Decades, if you're talking about detailed scientific study with modern instruments. We've sent spacecraft to comets. We've analyzed their spectra. We've measured their orbits. We've photographed their nuclei up close. We've even landed on one, which was a remarkable achievement in itself. So we know a lot about comets. Our solar system's comets, anyway. We understand their basic composition, mostly water ice, with frozen carbon dioxide, carbon monoxide, and other volatiles mixed in. We know how they behave as they approach the sun, how they sublimate, how they form comas and tails, how their activity varies with distance. We understand their origins, mostly in the distant Kuiper belt, or the even more distant Oort cloud. But here's the thing, all of those comets are related. They're all part of our family. They all formed from the same primordial material that created the sun and planets. They're all about 4.6 billion years old. They all formed under roughly the same conditions, in the same chemical environment. Which means that when we study solar system comets, we're learning about one specific example of planetary system formation. Ours. We're learning about the conditions in our particular protoplanetary disk, the chemical composition of our particular stellar nursery, the specific processes that occurred here. That's valuable information, extremely valuable, but it's also limited. It's a sample size of one solar system, one formation history, one set of initial conditions. To really understand planetary formation as a universal process, to figure out what's fundamental and what's specific to particular environments, we need comparison cases. We need to study material from other solar systems and see how it's similar to and different from ours. That's what 3I Atlas offers. A rare point of comparison. It's not dramatically different from solar system comets, as far as we can tell so far. It has water ice. It has carbon dioxide and carbon monoxide. It sublimates when heated by the sun. It forms a coma. It develops jets. In many ways, it behaves like a comet should behave, like the comets we're familiar with. But there are differences. Subtle ones, perhaps, but differences nonetheless. That reddish color in the coma, suggesting long-term space weathering. Those metallic vapors, nickel and probably others, which are detectable but somewhat unusual. The specific ratios of molecules, which might differ slightly from what we see in solar system comets. the isotopic ratios, which we're still measuring, but which could reveal different formation conditions. Each difference, no matter how small, is a clue. Each similarity, too, tells us something. Together, they help us understand what aspects of comet formation are universal and what aspects depend on local conditions. For example, if 3I Atlas has roughly the same water to carbon dioxide ratio as solar system comets, that suggests this ratio is fairly standard across different protoplanetary disks. Maybe it's determined by fundamental physics and chemistry. The temperatures and pressures at which these ices condense are similar everywhere. That would tell us something important about planetary formation in general. But if the ratios are different, if 3I Atlas has more carbon dioxide relative to water, say, then we learn that formation conditions can vary significantly from system to system. Maybe the star it formed around was hotter or cooler than our sun. Maybe the disk was more or less dense. Maybe the chemical composition of the original gas cloud was different. Each possibility opens up new questions and new avenues of research. The same applies to other measurements. Isotopic ratios, the relative amounts of different isotopes of elements like hydrogen, carbon, oxygen, can tell us about the conditions in the molecular cloud where the parent star system formed. If 3I Atlas has different isotopic ratios than solar system comets, it means it formed from material with a different chemical history, possibly in a different region of the galaxy, where stellar nucleosynthesis had produced different element abundances. By contrasting it with solar system comets, we glimpse other ways planets might form. We see variations on the theme. We learn that while the basic process, gas cloud collapses, disk forms, objects coalesce, might be universal, the details can vary. The temperatures, the densities, the chemical compositions, the timescales. All of these can differ from system to system, and that diversity is important to understand. Because when we look for planets around other stars, when we try to understand what kinds of worlds might exist out there, we need to know what range of conditions is possible. We need to know how much variation there can be in planetary system formation. 3I Atlas is one data point in that vast parameter space. One example of how things can go in a different stellar environment. It's not dramatically alien. It's recognizably a comet, following familiar physics, but it's not identical to our comets either. It's a variation, a different note in the same chord. And maybe that's the most interesting finding. Not that interstellar objects are wildly different from what we're used to, but that they're subtly different. That planetary formation is a robust process that produces similar outcomes in different places, but with variations in the details. That the universe has themes and variations, not just one-note repetition. The chemistry might differ. The behavior might differ. Not dramatically, perhaps. Not in ways that would be obvious at a glance, but in ways that careful measurement and analysis can reveal. In spectral lines that are slightly shifted, in molecular ratios that are just a bit off from what we expect, in isotopic signatures that tell of different formation histories. These subtle differences are where the science happens. They're where we learn about the diversity of the galaxy. They're where we glimpse, as the saying goes, other ways planets might form. We can't visit other planetary systems to study them directly, but we can study the debris they've cast out, the wanderers they've sent into the galaxy, And by comparing those wanderers to our own objects, we can start to build a picture of what's universal and what's variable in the process of planetary formation. 3i Atlas is helping us build that picture, one spectral measurement at a time, one isotopic ratio at a time, one subtle difference at a time. It's teaching us about somewhere else by allowing us to compare it with here. And in that comparison, in that contrast, we're learning not just about 3i Atlas specifically, but about the galaxy more broadly, about the diversity of environments where planets form, about the range of possibilities that exist in our cosmic neighborhood. A rare point of comparison. That's what makes it valuable. Not just interesting in itself, but informative about the broader patterns and variations in how planetary systems come to be. Some speculative ideas suggest alternative origins, but most evidence points to a natural, icy comet. The mystery invites curiosity without fear. Science thrives on gentle questions. Whenever we discover something unusual, something from outside our familiar context, speculation begins. That's natural. That's human. We encounter something we don't fully understand, and our minds start exploring possibilities. Some of those possibilities are conventional, grounded in well-established physics. Others are more exotic, pushing into less charted territory. 3i Atlas has generated its share of speculation. Some researchers have wondered whether its composition might be more unusual than it appears, whether it could be a fragment of a larger object rather than a primordial planetesimal, whether there might be something unexpected in its internal structure, whether it could represent a class of interstellar objects we haven't encountered before. And yes, as with Oumuamua before it, there have been more exotic speculations. Could it be artificial? Could it be a probe or a vessel from another civilization? Could it be something deliberately sent rather than naturally ejected? These are the kinds of ideas that capture headlines and imagination. They're exciting to think about. They tap into our deep curiosity about whether we're alone in the universe, whether other intelligences exist, whether we might someday encounter evidence of them. But here's the important thing. Most evidence points to a natural, icy comet. The observations we've made, the spectroscopy, the photometry, the orbital analysis, the behavior as it approaches the sun, all of these are consistent with a comet, a natural object, ice and dust and rock, following physics, responding to sunlight exactly as we'd expect an icy body to respond. There's nothing in the data that requires an exotic explanation, nothing that can't be accounted for by straightforward comet physics and chemistry. It's behaving like a comet. It's composed of materials we'd expect in a comet. It's following a trajectory consistent with natural gravitational dynamics. The exotic explanations, while they can't be ruled out with absolute certainty, because absolute certainty is rare in science, aren't necessary. They don't explain the observations any better than the simple explanation. It's a comet. An interstellar comet, yes, which makes it rare and interesting, but still fundamentally a comet. And that's okay. That's actually wonderful. Because natural explanations don't diminish wonder. A comet from another star system, carrying ancient ice, passing through our neighborhood for the first time in billions of years. That's remarkable enough without needing anything exotic added to it. The mystery invites curiosity without fear. That's the key phrase there. Curiosity without fear. We can be curious about 3i Atlas, We can wonder where it came from, what it's made of, how it compares to our comets, what it can teach us. We can ask questions. We can make observations. We can speculate and theorize and test our ideas against data. But we don't need to be afraid, not of the object itself. We've already established it poses no threat, but also not of the implications, not of what it means or doesn't mean, not of whether the answers will be unsettling or challenging. Science thrives on gentle questions, not aggressive certainties, not dogmatic insistence, just gentle, curious questions. What is this? Where did it come from? How does it work? What can it teach us? Those questions don't require dramatic answers. They don't need exotic explanations or paradigm-shifting revelations. Sometimes, often, actually, the gentle questions have straightforward answers, and the straightforward answers are just as fascinating as any exotic alternative would be. 3I Atlas is probably a comet, a natural icy comet from another star system. That's the most likely explanation given the evidence, and that explanation is wonderful. It tells us about planetary formation, about interstellar space, about the long-term survival of ice in the cosmic environment, about the interconnectedness of the galaxy. But we'll keep looking, keep measuring, keep analyzing, because that's what science does. It holds its conclusions lightly, always ready to update them if new evidence emerges. It entertains multiple hypotheses and lets the data arbitrate between them. It remains curious without being committed to any particular answer ahead of time. The speculative ideas, the alternative origins, the exotic possibilities, they have their place. They push us to look more carefully, to gather better data, to consider what additional observations we'd need to distinguish between different explanations. They keep our minds open to possibilities we might not have considered, but they don't dominate the discussion. Most astronomers studying 3I Atlas are focused on the straightforward work of characterizing it as a comet, measuring its size, its composition, its activity levels, comparing it to solar system comets, building models of its behavior, asking and answering the gentle questions that gradually accumulate into understanding. There's no fear in that work, no anxiety about what the answers might be, just patient curiosity, methodical observation, careful analysis, the kind of science that doesn't make dramatic headlines, but slowly, steadily expands our knowledge. And maybe that's a good model for how to think about mysteries in general. With curiosity, yes. With wonder, absolutely. But without fear. Without needing the answers to be exotic or unsettling. Without treating every unknown as a source of anxiety. 3I Atlas is a mystery, in the sense that we don't know everything about it yet. We don't know exactly where it came from, precisely how old it is, what star it originated around. We're still measuring its composition, still analyzing its behavior, still building our understanding. But it's a gentle mystery, an invitation to curiosity, a chance to learn something new about the galaxy, and the likely answer that it's a natural comet, following natural laws, carrying natural materials, is no less wonderful for being natural. The mystery invites curiosity without fear. That's the spirit in which to approach it. Curious, patient, open to whatever the data tells us, but not anxious about the implications. Just curious, gently curious. The way you might wonder about a traveler you met briefly, where they came from and where they're going, without needing those answers to change your understanding of the world. Science thrives on gentle questions, and 3i Atlas, whatever its ultimate story turns out to be, is answering those gentle questions, one observation at a time. We still don't know its exact shape, its original star, or how far it has truly traveled. Its unknown history gives it a serene kind of cosmic anonymity. There's something peaceful about not knowing everything, about having gaps in our knowledge, mysteries that remain unsolved, questions that linger without immediate answers. It gives space for wonder, room for imagination, permission to be uncertain. 3i Atlas embodies this perfectly. We know a lot about it. We've covered many of those facts already. We know it's interstellar. We know it's a comet. We know roughly how big it is, what it's made of, how it's behaving as it passes through our solar system. But we don't know everything. Far from it. We don't know its exact shape, for instance. Is it roughly spherical, like a lumpy snowball? Is it elongated, perhaps like Oumuamua turned out to be? Is it irregular, with one end larger than the other? Is it relatively smooth, or heavily cratered from billions of years of micrometeorite impacts? The coma surrounding it makes precise shape determination difficult. We're seeing a fuzzy cloud of gas and dust, not the clean silhouette of the nucleus itself. We can estimate size, but shape, that requires closer observation than we're able to make at these distances. We don't know its original star. We can trace its trajectory backward, but as we discussed earlier, billions of years of subtle gravitational deflections make it impossible to pinpoint exactly where it came from. It entered our solar system from the general direction of the galactic center, but that's an enormous region of space containing billions of stars. Which one was its home? We can't say. Maybe we'll never be able to say. We don't know how far it has truly traveled. We know it's been wandering for billions of years, but that doesn't translate directly into distance. It might have been moving fairly quickly, covering vast stretches of the galaxy. Or it might have been moving more slowly, taking a more meandering path, drifting through a smaller region of space over those billions of years. Without knowing its velocity, history, and trajectory in detail, which we can't reconstruct, we can't calculate the total distance traveled. And there are other unknowns. Has it passed through other solar systems before ours? Probably, statistically speaking. But which ones? How many? How close did it come? We don't know. Did any of those close passages significantly alter its composition, sublimating some of its ice before it reached us? Possibly. We can't be certain. Does it have a companion? Some objects in space are binary systems, two objects orbiting each other. Is 3i Atlas alone, or is there a partner object we haven't detected? We don't know. The coma makes it difficult to tell if there's more than one nucleus. Is it rotating? Almost certainly. Most objects in space rotate. But how fast? What's its rotation period? And does it tumble as it rotates, or does it spin more stably around a single axis? We're still working on answering these questions. All of these unknowns give 3i Atlas a certain anonymity. We can see it, we can study it, but we can't fully identify it, can't place it completely, can't reconstruct its full history, or predict exactly what will happen to it after it leaves our solar system. It remains, in a sense, unknown, a wanderer without a complete story, a traveler without a clear point of origin or final destination. And maybe that's appropriate. Maybe that's even beautiful in its own way. This object has been traveling for so long, through so much empty space, that its history has become partially erased. The details have blurred, the specific facts have been lost to time and distance. What remains is the essential mystery, a visitor from elsewhere, from somewhere out there, from a past so distant and a journey so long that the particulars no longer matter as much as the simple fact of its existence. Its unknown history gives it a serene kind of cosmic anonymity. Serene, that's an interesting word choice. Not mysterious in a frightening way, not unknown in an unsettling way. Just serene, peacefully anonymous, comfortable with its own unknowability. Like a monk who has taken a vow of silence, 3i Atlas isn't telling us its full story, not because it's hiding anything, but because the story has been lost to time. The details have sublimated away, metaphorically speaking, leaving only the essential presence, an ancient wanderer, passing through, carrying mysteries we may never fully solve. And in a strange way, that makes it easier to contemplate as you drift towards sleep. You don't need to know everything. You don't need complete answers. The gaps in knowledge aren't frustrating, they're peaceful. They give your mind room to wonder without the pressure of needing to arrive at conclusions. We still don't know its exact shape. That's okay. We can imagine it might be any of various shapes: spherical, elongated, irregular. Each possibility is interesting in its own way. We still don't know its original star. That's okay. It could have come from any of billions of stars. Each one is a possible origin point. The uncertainty doesn't diminish the wonder. We still don't know how far it has truly traveled. That's okay. Whether it's crossed half the galaxy or meandered through a smaller region, the journey has been unimaginably long. The exact distance doesn't change the essential fact. It has traveled far and for long and is now here. Anonymous wanderer. That's what it is. Not anonymous in the sense of being unnoticed. We've definitely noticed it, cataloged it, studied it. But anonymous in the sense of having an unknown backstory, unknown origin, unknown total journey, unknown future beyond our solar system. It passes through our lives briefly, this anonymous wanderer. We observe it for a few months, maybe a year. We gather what data we can. We learn what we're able to learn. And then it continues on its way, carrying its mysteries with it, returning to the serene anonymity of interstellar space. There's something comforting about that, about the fact that the universe contains travelers we can observe but never fully know. Mysteries we can appreciate without needing to solve. Unknowns we can contemplate without anxiety. As you drift deeper towards sleep, let 3i Atlas keep its anonymity. Let it remain partially unknown. Let its exact shape, its original star, its true distance traveled stay mysterious. Those unknowns don't diminish it. If anything, they enhance it. They give it depth. They allow it to represent all the vast unknowns of the galaxy, all the mysteries that remain beyond our ability to fully catalog and understand. An anonymous wanderer, serene in its cosmic anonymity, passing through, briefly visible, soon to fade back into the unknown from which it emerged. And that's enough. That's more than enough. To know that it exists, that it's here, that it's carrying ancient ice from somewhere else, to observe it while we can, to wonder about it without needing all the answers. The observation window is brief. It's moving too fast to stay long in our telescopes. Its fleeting presence reminds us that beauty often visits only once. everything ends. Every observation window closes. Every visitor eventually departs. That's not melancholy. It's just time passing, which it always does. But there's something about 3i Atlas that makes this temporariness particularly poignant. It's moving too fast to stay long. That hyperbolic orbit we discussed earlier, it means the object is sweeping through our solar system on a trajectory that won't bring it back. It came from interstellar space, it will return to interstellar space, and in between, there's only this brief window when it's close enough and bright enough for us to observe in detail. How long is that window? Maybe a year total. Perhaps a bit more if we're lucky, and it remains active and bright as it recedes. But compared to the billions of years it has been traveling, compared to the billions more it will continue traveling, this year is nothing. A blink. A brief moment of visibility in an otherwise invisible journey. Astronomers are working quickly. Every clear night is an opportunity. Every telescope that can be pointed at 3i Atlas is pointed at it, gathering photons, recording spectra, measuring positions, tracking changes, because they know this opportunity won't last. Soon, and soon in astronomical terms might be months, but still, soon enough, 3i Atlas will move too far away. The coma will fade as it moves beyond the sun's warming influence and returns to the cold of deep space. It will become too dim to observe with most telescopes. The smaller details will become impossible to resolve. Eventually, even the largest telescopes will lose it against the background stars, and then it will be gone, back to being invisible, back to being one of countless objects drifting through interstellar space, too distant and dark for us to see. We'll have the data we collected. The observations will remain, archived, available for future analysis. Scientists will continue studying that data for years, extracting information, refining models, understanding more about what this visitor can teach us. But the direct observation, the real-time tracking of an active interstellar comet as it passes through our neighborhood, that will be over. That window will have closed. Its fleeting presence reminds us that beauty often visits only once. Not just beauty in the aesthetic sense, though there is beauty in the images of this comet, in its glowing coma and its delicate jet, but beauty in the broader sense, remarkable things, rare things, things worth paying attention to. These don't always linger. Sometimes they pass through quickly. Sometimes you get one chance to observe them, to appreciate them, to learn from them. And if you miss that chance, it's gone. This is true in life generally, not just in astronomy. Moments pass. Opportunities close. Beautiful things are often temporary. The sunset you happen to witness, spectacular in its colors. You could see another sunset tomorrow, certainly, but not that particular one, with those specific clouds and that exact lighting. That moment exists once and then passes into memory. 3i Atlas is like that, scaled up to cosmic proportions. It's a specific, unique object with a specific, unique history, passing through our specific, unique moment in time. And we get to see it for this brief window, this one observation period. This one passed through our neighborhood. It won't come back. Not in our lifetimes. Not in 100 human lifetimes. Not ever, actually. Its hyperbolic orbit means it's leaving the solar system permanently. This is the only time humanity will ever observe 3i Atlas. The only time these particular photons, bouncing off this particular object, will make their way to our telescopes. That could feel sad. And maybe there's a touch of bitter sweetness to it, but mostly it's just the nature of things. Beautiful things are often temporary. Rare visitors don't stay long. The observation window is brief because the universe is vast, and objects are moving, and we only get to see small fractions of the larger patterns. But that temporariness, that fleeting quality, can actually enhance appreciation rather than diminish it. When you know something won't last long, you pay closer attention. You don't take it for granted. You don't assume you can study it later at your leisure. You observe it now while you can, because you know the window is closing. Scientists believe many such interstellar travelers pass through unnoticed, too small or dim to see. Our skies may be busier than we think, filled with silent passing guests. For every interstellar visitor we detect, how many do we miss? That's the question that keeps astronomers thinking, calculating, extrapolating. We've found 3 confirmed interstellar objects so far, 3 in the span of 8 years of really watching for them with modern survey systems. 3 visitors from beyond our solar system that we noticed and tracked and confirmed. But those are just the ones we saw. Just the ones that happen to be bright enough, large enough, or close enough for our telescopes to detect. Just the ones that passed through regions of sky we were actively surveying. Just the ones that arrived when our detection systems were capable of spotting them. What about all the others? Statistical models based on the detection rate so far and on assumptions about how many objects we're likely to miss suggest something remarkable. Interstellar visitors might be passing through the inner solar system regularly, not rarely, not once a decade or once a century, but multiple times per year, maybe even monthly or more frequently, depending on whose models you believe. Most of them, though, are too small or too dim for us to see. They're there, passing through, following their hyperbolic trajectories, carrying their ancient ice from one nowhere to another nowhere, briefly transiting our neighborhood, but invisible to us, unnoticed. It's like standing in a crowded plaza with your eyes closed. You know, intellectually, that there are people walking past you constantly. You might hear some of them, might feel the air move as someone passes close, but most of them go by completely unnoticed, and you'd have no way to know how many there were without opening your eyes. We're slowly opening our eyes. Our survey telescopes are improving. Our detection algorithms are getting better. Our follow-up observation networks are more coordinated. With each improvement, we catch a few more of the visitors who previously would have passed unnoticed. But we're still missing most of them. An object has to meet several criteria to be detected. It has to be large enough to reflect sufficient light. It has to pass close enough to Earth, or at least close enough to the sun to develop an active coma that increases its brightness. It has to cross a patch of sky that we're actively surveying at the right time. And even then, it has to stand out enough from background stars and known solar system objects for our detection algorithms to flag it as unusual. That's a lot of requirements. Many objects won't meet all of them. A small, dark object passing through the outer solar system will almost certainly miss it. An object that passes through quickly without getting close to the sun, so it never develops a bright coma. Easy to miss. An object that transits a patch of sky we weren't surveying that week? Gone before we know it was there. Our skies may be busier than we think, much busier, filled with silent passing guests who arrive, drift through, and depart without announcement. Wanderers from other star systems, each carrying their own cargo of ancient materials, each with their own billion-year history, each just as interesting as the three we've managed to confirm. But we don't see them, can't see them. Our instruments aren't sensitive enough, our surveys aren't comprehensive enough, our coverage isn't complete enough, so they pass through invisibly, and we continue on not knowing they were ever here. It's humbling when you think about it. We like to believe we're watching the skies carefully, that we have a good handle on what's out there, what's moving through our cosmic neighborhood. And we're better at it than we've ever been. Our observational capabilities have improved dramatically over the past few decades. But the universe is still mostly hidden from us. Most of what's happening, most of what's passing by, remains unobserved. We catch glimpses. We detect a fraction of what's there. But the full population of interstellar visitors, that's still largely invisible. The three we found, Oumuamua, Borisov, Atlas, they're likely the tip of an iceberg. The bright examples, the lucky detections, the objects that happen to meet all the criteria for visibility and happen to be caught by our surveys. Behind them, unseen, there might be dozens more passing through each year. Small ones, dark ones, objects on trajectories that don't bring them close to Earth, objects that slip through the gaps in our observational coverage, silent passing guests. That's what they are. Not invisible in principle. If we had perfect observation capabilities, we could see them, but invisible in practice, given the limitations of our current technology and coverage. And there's something almost poetic about that, about the idea that the space around us might be much more dynamic than it appears, that while we go about our days, while we sleep and work and live our lives, ancient travelers from distant star systems are constantly passing through our neighborhood, unnoticed, unrecorded, just passing by. It changes the feeling of space, doesn't it? Instead of being mostly empty, mostly static, it becomes more like a thoroughfare, a pathway that wanderers cross regularly. Our solar system isn't isolated. It's part of a flow, part of the galaxy's circulation system, where objects ejected from one system drift until they pass through another. We happen to be in one of those others, and objects drift through regularly. We just don't see most of them. Maybe that's okay. Maybe we don't need to see every visitor to appreciate that they're there. Maybe knowing that our skies are busier than we can observe, that silent travelers are constantly passing through unseen, is enough. It adds mystery. It adds awareness of our limitations. It reminds us that there's always more happening than we can detect. The three we've confirmed are precious because they're rare in our experience. But they might not be rare in reality. They might just be the visible representatives of a much larger population, the ones we happen to catch, the ones who announce themselves loudly enough for us to notice. And for all the silent passing guests we'll never see, they continue their journeys undisturbed by our ignorance. They don't need to be observed to exist, don't need to be cataloged to matter. They're out there, drifting through, whether we notice them or not. Our skies may be busier than we think, filled with wanderers, filled with ancient ice and rock from elsewhere, filled with stories we'll never know and histories we'll never trace, filled with silent, passing guests who arrive and depart without fanfare, following mathematical trajectories through the space we think of as ours, but which belongs, really, to no one. And maybe as you drift towards sleep, that's a comforting thought. That the universe is more active than it appears, more filled with travelers and motion and passage. That above us, around us, through the solar system we call home, wanderers from elsewhere are constantly moving through, silent, mostly unseen, but there, always there, passing guests in the night. Philosophically, 3i Atlas reminds us that our solar system is not isolated. It's part of a galactic flow. Even across light years, there are connections, quiet exchanges of matter and motion. There's a tendency to think of solar systems as islands, discrete, self-contained, each one orbiting its star in relative isolation, separated from other systems by vast gulfs of empty space. And in one sense, that's accurate. The distances between stars are enormous, light years, trillions of kilometers. So much empty space that crossing it seems almost impossible. But 3i Atlas tells a different story. Its very existence, its passage through our neighborhood, suggests that solar systems aren't quite as isolated as they might seem. They're connected. Not directly, not obviously, but connected nonetheless through a slow exchange of material that occurs over vast timescales. Think about it. Billions of years ago, material in one star system was ejected. It traveled through interstellar space for eons, and now it's here, in our system, briefly visible before, continuing on. That's a connection. A physical transfer of matter from one stellar environment to another. A thread, however thin, linking systems across light years and billions of years. And 3i Atlas isn't unique in this. As we discussed, interstellar objects likely pass through regularly. Each one is another connection, another transfer, another exchange of matter between systems. Our own solar system participates in this exchange, too. During its formation, it almost certainly ejected countless small objects, planetesimals that were flung out by gravitational interactions with forming planets. Those objects are out there now, wandering through the galaxy. Some of them have probably passed through other solar systems by now. Some might be passing through other systems right at this moment, being observed by other astronomers, if such exist, the way we're observing 3i Atlas. So we're not just receiving visitors, we're sending them too. It's an exchange, a circulation. Matter moves between systems slowly over billions of years, carried by objects following hyperbolic trajectories. It's part of a galactic flow. That's the philosophical insight here. The galaxy isn't a collection of isolated islands. It's more like an ecosystem, a connected system where matter circulates, where material formed in one place eventually travels to others, where the boundaries between our material and their material are fuzzy and permeable. Even across light years, there are connections. Not the immediate connections of radio signals or light beams. Not the kind of connections we usually think about, but physical connections, material connections, objects that formed in one system physically arriving in another. Atoms and molecules making the journey from star to star, carried inside frozen wanderers. These are quiet exchanges of matter and motion. No drama, no fanfare. Just the slow, patient transfer of material that occurs naturally as a consequence of planetary system formation and gravitational dynamics. Some material gets ejected. It wanders for a while. Eventually, it passes through another system, then continues on. Over billions of years, over the full lifetime of the galaxy, this exchange becomes significant. Every star system is constantly receiving and sending out material. The galaxy mixes itself slowly through these wandering objects. Material that formed in one stellar environment eventually gets distributed, however thinly, across vast regions of space. There's something profound about that, about the realization that we're not isolated, that the atoms in your body, which formed in our solar system about 4.6 billion years ago, are chemically related to atoms currently wandering the galaxy in countless interstellar objects, and that some of those wandering objects occasionally pass through here, briefly mixing their atoms with ours before moving on. Its connection on a time scale so long that it's almost meaningless to individual humans. But it's still connection, still exchange, still evidence that solar systems aren't truly isolated, but are parts of a larger whole. 3I Atlas reminds us of this. Its presence here, after billions of years of travel, after formation in a completely different stellar system, is proof of galactic interconnection. Proof that matter flows between stars. Proof that our solar system receives visitors from elsewhere, and has likely sent countless visitors to other systems in return. We're part of a galactic flow, not a powerful flow, not a rushing river, more like a gentle circulation, a slow mixing, a patient exchange that occurs over time scales longer than the age of planets, but which, when you step back and look at the full picture, connects everything. Even across light years, distances so vast that light itself takes years to cross them, there are connections, material connections, objects carrying atoms from one place to another. The galaxy connects to itself through these wanderers, these messengers, these fragments of one place appearing in another. And maybe that's a comforting way to think about the galaxy. Not as a vast empty space with scattered islands of matter, but as a connected system, a community of stellar systems exchanging material. Slowly, patiently, but genuinely connected through the quiet flow of interstellar objects. Our solar system is not isolated. We receive visitors like 3I Atlas. We've probably sent out countless visitors of our own. We participate in the galactic circulation. We're part of the flow. That makes us less lonely in a cosmic sense. We're not adrift in emptiness. We're nodes in a network, participants in an exchange, members of a community that operates on timescales we can barely comprehend, but which connects us nonetheless to stellar systems we'll never directly observe. It's part of a galactic flow, matter and motion exchanged quietly across light years. Connections maintained not through signals, but through the physical presence of wandering objects. A slow mixing of the galaxy's material through billions of years of patient circulation. And right now, 3I Atlas represents one moment in that flow. One connection made visible. One thread in the vast web of galactic exchange that usually remains invisible, but which occasionally becomes observable when a wanderer passes close enough for us to notice. We're not isolated. We're connected, part of something larger, participants in a flow that spans the galaxy and operates over billions of years. And that gentle philosophical realization that even across light years there are connections, quiet exchanges of matter and motion, might be the most profound thing 3I Atlas has to teach us. The deepest mystery remains. Where exactly did it come from? And what story of another world does it carry within its ices? Its silence is its gift, a riddle that invites wonder, not worry. We've reached the end of our list, but not the end of the questions. Many ways, we're just at the beginning, because for all that we've learned about Three Eye Atlas, for all the observations we've made, and data we've collected, and conclusions we've drawn, the deepest questions remain unanswered. Where exactly did it come from? We know, somewhere in the direction of the galactic center, somewhere billions of years ago, from some star system we can't identify. But which star? What kind of star? Was it larger or smaller than our sun? Hotter or cooler? Did it have planets? How many? Were those planets similar to ours or wildly different? We don't know. Can't know. The trail is too old, the deflections too many, the uncertainties too large. Three Eye Atlas carries its origin story in its trajectory, but that story has been scrambled by billions of years of gravitational interactions, rendered unreadable by time and distance. And what story of another world does it carry within its ices? What can the frozen molecules tell us about the protoplanetary disk where this object formed? What were the temperatures like, the pressures, the chemical composition? What other objects formed alongside it? Did any of them become planets? Are there worlds orbiting Three Eye Atlas's home star right now? Worlds that formed from the same disk of gas and dust? Worlds that might have life, intelligence, civilizations? The ice knows. Every molecule, every isotopic ratio, every chemical compound preserved in that frozen nucleus carries information about formation conditions. But we can only read a fraction of that information. Some of it will remain locked away forever, inaccessible without sample return missions. We'll never be able to launch. The deepest mystery remains. And you know what? That's okay. That's more than okay. That's actually perfect. Because its silence is its gift. Not the silence of having nothing to say, but the silence of mysteries that remain unsolved. Questions that linger. Unknowns that persist despite our best efforts to know. In our daily lives, we're often frustrated by unanswered questions. We want complete information. We want to understand everything fully. We want certainty and closure and comprehensive explanations. But Three Eye Atlas offers something different, a riddle that invites wonder, not worry, a mystery that enhances rather than frustrates. Questions that make it more interesting, not less. We don't know where exactly it came from. That means we can wonder. We can imagine different possibilities. We can think about various stellar environments and consider which might have produced this particular wanderer. We can let our minds explore the space of possibilities without being constrained by definitive answers. We don't know what story its ices tell completely. That means there's still more to learn. The research continues. Future observations might reveal new details. Better instruments might unlock information currently inaccessible. The story is still being written, still unfolding, still surprising us. And maybe that's the state we should approach mysteries in general. Not with anxiety about what we don't know, but with curiosity about what we might discover. Not frustrated by gaps in knowledge, but excited by opportunities for future understanding. Not worried by unknowns, but wondering about them. Three Eye Atlas invites wonder. It presents us with a beautiful puzzle, a visitor from another star system, carrying ancient ice, releasing gases that hint at its composition, but don't fully reveal its origins. We can study it. We can learn from it. We can gather data and build models and refine our understanding, but we can't know everything, can't trace it back to its specific birth star, can't fully read the story written in its chemical composition, can't predict with certainty where it will go next or what it will encounter on its continued wandering. And that's the gift, the invitation to wonder without needing complete answers, to appreciate mystery without anxiety, to let questions remain open without feeling unsettled by them. As you drift towards sleep now, you can carry 3i Atlas with you, not as a collection of facts to remember, but as a feeling, a sense of cosmic wonder, an appreciation for mysteries that remain mysterious, a comfort in not knowing everything. It came from somewhere out there. It's going somewhere out there. In between, it passed through here, and we were fortunate enough to notice it, to observe it, to wonder about it. The deepest mystery remains. Where exactly did it come from? What story does it carry? We don't know. We may never know completely, and that's perfectly, beautifully okay. Its silence is its gift, a riddle that invites wonder, not worry, a mystery that enriches rather than troubles, an unknown that makes the universe more interesting, not less. So let the questions linger, let the mystery remain. Let 3i Atlas keep its secrets while sharing just enough to spark our curiosity. Let it be what it is, a visitor from elsewhere, carrying unknowns, passing through briefly, leaving us with wonder. And so our ancient visitor continues on its way, fading from our telescopes now, returning to the cold and dark, carrying its mysteries back into the space between stars. We had a brief window to observe it, to study it, to wonder about it. And now that window is closing. But what 3i Atlas leaves behind is a gift of perspective, a reminder that our solar system isn't isolated, that the galaxy is more dynamic than it appears, that ancient wanderers pass through regularly, connecting stellar systems across vast distances and timescales. We're part of something larger, part of a galactic flow, part of an exchange of matter and motion that has been happening for billions of years and will continue for billions more. And perhaps most importantly, 3i Atlas reminds us that mystery is not something to fear. The unknown is not threatening. Questions without complete answers are not frustrating. They're invitations. Invitations to wonder, to imagine, to remain curious, to appreciate the vastness and complexity of the universe we inhabit. You don't need to know everything to rest peacefully. You don't need all questions answered to drift into sleep. Sometimes the mysteries are the most comforting part, the questions that remain open, the unknowns that persist. They give the universe depth. They remind us there's always more to discover, more to wonder about, more to appreciate. So rest easy tonight, knowing that ancient travelers are drifting through the darkness, that the galaxy is more connected than it seems, that mysteries remain and will continue to remain. Rest knowing that wonder is always available, that curiosity can be gentle rather than urgent, that not knowing everything is perfectly, beautifully okay. 3i Atlas came from somewhere beyond. It's returning to somewhere beyond. And for this brief moment, it passed through here, leaving us with data and observations, and most importantly, with wonder. Sweet dreams, friend. May your rest be as peaceful as the long drift of ancient wanderers through interstellar space. May your sleep be as deep as the cosmic mysteries that remain unsolved. And may you wake refreshed, still curious, still wondering, still appreciating the vast and beautiful universe we're fortunate enough to inhabit. Good night.